All right, so I decided to create what is essentially a version of this previous design I just talked about, because obviously I'm recording it roughly at the same time for my energy crisis series fix. Now, we all love these cars, and we know about hydrocarbon uses. It's just so great. And I was like, I came up with a way to basically stop carbon in the series from coming out of your exhaust for the majority of it by utilizing effectively high heats and material charge field extractions. So there you go, which is work energy produced in the engine, so you have to add it into the overall efficiency, even though it's not work energy to send it down the road, but I never gave a shit about that part. But now we're going to get into the windmill thing that I was talking about, and then the waste heat extractor, generator, radiator concept. Look, this one's cool, but I needed a battery that does even better. So this windmill instead turned into a basically blower design for a battery. It's not even a joke. So, our bones. Good old bendy, pretty stiff bones, quite porous. I was like, okay, so if I use iron with a, potassium or something similar with the compounds that we're seeing produce the electricity in plants, I would love to give you those studies that came out recently, and in fact a few YouTubers have already done videos on them. I don't feel comfortable linking them because I don't know if they want me to, but you can definitely look it up. But there you go. They're really cool. I love that idea, but it's like, look, we just need a synthetic rough kind of. Actually, I went with the organic, truthfully, with a basic structure that is the bone. Okay, so I use plasma deposition, creating a very porous structure of the iron that would then have a charge of this, like powder coating is used to deposit certain things and adhere it to the structure. So if I happen to do that with iron when it's fairly porous and I have the correct little structure already laid out for it to adhere to, then I can then add in this, if you don't know, anybody out there probably does, though, this potassium tends to interact with water pretty substantially. It tends to separate it. There's latent humidity in the air pretty much everywhere as far as I'm aware. Not all the time, but almost everywhere, and it gives me a degree of heat, and bones, when they're like this, if we have that other, because it's creating with light photon, but it's really just heat. Okay, if you don't know, or if you reflect it an IR correctly with the right degree of wavelength, then you get a regular blue light or a higher degree of wavelength that can help you with creating that electricity by electron removal and electron add-on, which is what I was using in the band gap, solar panel idea. Okay, so as a result of that, then I'm able to, which is why it's like I don't have to prove that to you; it's already known. So, but then I can do literally the same for these compounds, and this heat will allow for expansion and contraction, which is piezoelectrics. And those electricities, electrons, and I remove it, and then as it goes through, and I have this, potassium or something similar, as it goes across, it produces an explosion of hydrogen and oxygen, which typically means an electron flow battery with heat, which heat, by the way, needs to get involved into this radiator, which is now being funneled into this battery because that's sucking in air for me to gain a greater and greater degree of efficiency. Now, oxygen also happens to be an incredible helper of this hydrogen, like regular air coming in. And so as it goes through and it filters through, which is a filter battery for our air, it can work to incredibly high heats. Now, high heats, that's fine. Truthfully, from my perspective, in fact, higher heats is better in all aspects, because this waste heat generator is pretty good at keeping it cool. And same thing with that fan shroud, it's still a waste heat generator that can be used. So it's like, look, this battery, and it's like it holds a charge on its own right if you do it correctly, which is actually more capacitive, if we're being honest. Then when you flow it through, it becomes an electron flow battery, which will go into the band gap fluid for the solar panel on the hood of your car and the roof of your car and the trunk of your car, because that's fairly easy to replace. They're fairly flat. And so as a result of them being fairly flat, then it's pretty easy to just stick this on there. So I was like, this is not a bad idea. And so I was like, all right. No, I just need to get the right binder material that can handle these higher heats, but I don't really need it to be too hot. In fact, that's not really what I'm trying to do. But what it means is it's like, right, I'm cooling everything down with radiators, but also I'm creating a great degree of electricity, and these batteries will, more like a capacitor, hold charge, but then not fully. They're like a generator, really more as well, as they contracts and expands in these little micro/nano, maybe, smaller micron ranges. They rapidly cool, but they also rapidly expand and rapidly cool and rapidly expand and rapidly cool and rapidly expand, producing a lot of electricity. Good old electricity with a band gap coolant that runs through it, which helps improve its, just like with the solar panels, degree of electron flow, producing heat. Again, that is correct. And then it goes into the radiators, and then it goes off into the, more electricity. It's not going to make more. There's no more. Okay, there's only a certain amount you're going to get from this. Anybody that's out there that's like, no, you're making more. No, at most, I theorize this could be in the 80-ish% range of efficiency for these battery generator designs, which is a capacitor/battery, because with the electron gap, it is only a battery, because it's a fluid solid-state battery, capacitor type, because it has a field effect, and then those also have their own capacitive charge, but because it's not flowing and it doesn't have any real ability to flow, it has a held charge, not a only capacitive, like a supercapacitive charge, which means it can dump that initial charge. That creates heat. It allows for the flow to start. That helps you get going. Everything starts its process off. As it starts getting going, it starts having an easier and easier effect on this windmill that pushes the air greater and greater degrees through this battery thing, electron flow thing. I don't know really what you'd call that. It's quite a few things in one, truthfully. But it also means the solar panels are cooled and more efficient, and the radiator continues to keep giving you nice electricity to a point. You can only gain back some of the loss. That's really all it's for. It's nothing more than that. Okay. Anybody out there? I can make electricity from the air, and it's like, actually, I designed it specifically for refrigerant use, from like refrigerant combos with a regular pump, as the refrigerant is in a soda bubble-like state in regular water or some other fluid. Then it would expand upon a area for the IR emitter technology that is helping cool our stuff like AC, but instead now they use IR And I was like, that would be a really easy way to just use this. This would be really simple, so that maybe it makes the pump a little less terrible. Okay, why not? You know what I mean? It's like, oh, I can maybe get the pump amount, and it's like, oh, right, yeah, no, I can probably, how much can I extract from that? How much can I concentrate realistically from a given area and volume, for like that? And you might be able to overrun that pump until it's reduced its heat in that area, and then it doesn't do that anymore. So there you go. That whole runs it until it's like it's too cold, and it's like, shucks. Well, all right. But then I was like, supercavitation? What's this thing? Plunk. Vacuum turbine. Whoop! More efficiency. Yay! It can go even colder before it goes. I don't do it no more. And so that's kind of where that ended up getting to on that design. So it's like, it's a fairly efficient heat pump for what it is. You know what I mean? Nice. I get a little bit of electricity, and technically, as long as there's still sun and that kind of thing. Which it's like, it was really just trying to make hyper efficient energy extractors from waste heat. Leave the kitty alone, puppy. The cat's been here before. The puppy's new. He doesn't know not to bark at the cat. Come here. Yeah. Anyways, day in the life of, But the point is like, it's a fairly efficient design, and that's actually a decent way to basically shine IR at my enemies in front of me and to my sides. Hey! Death laser you over there. Yeah, I'm just going to drive right next to you. Not really. No, not really. But, like, still, though, if I could. But, that's kind of the point I was trying to make. It's like, look, this would drive a vehicle if it didn't weigh too much and the batteries were performing adequately. I mean, they were properly designed that happened to produce quite a good degree of electricity through the air that's flowing through it, because the higher the flow of air, the more likely it is to continue this degree of electron generation. Okay, and so that's really what it was about. And it's like, my designs, I'm being hesitant because, of course, I'm not a chemist. I have no PhD. I'm just an enthusiast of science and technology, engineering and mathematics and all that. I say it's in the 3,000 degrees C, but that is also an iron combined with in a bone-like structure that utilizes piezoelectric expansional and contractional metamaterial, almost basically, but it's like, right, in plasma deposition, charge, dump it on, it then has this, I have a lack of electron, boom, I now have the ability to really stick this to it, and then it's like, right, then I still have the ability to add in all these other components, which are in their own right, or while organic, they usually don't survive very high temperatures, can be mimicked to survive high temperatures. In fact, we have these wonderful plastics that are metallic now and are also able to hold and have electricity flow through them. And so, turns out they have wonderful structures when you put them together that can increase with that potassium and the band gap and all this other stuff. Basically a very incredibly accurate replica of the very phenomenon we see in plant material, organic plant material, that survives in extreme degrees of heat, but we're not going to hit that. We're not trying to hit that. I mean, maybe in those little small areas of the micro or nano size little, bubble areas that this is really going to try and do its thing. It might hit that, but then air goes through and it does it again, it cools, and so eventually it'll probably wear down. Caveat, I don't know. So like there's that problem part. But it was also, I came up with this as a result of being like, iron cobalt with like severe, okay, so iron, again, same structure. I shove in cobalt with that charge thing, and then I'm like, pressurize it with a great degree of charge difference hydrogen. Because I was like, if I can make this into a spacesuit, because it would pretty much create electricity doing that, pretty much the same way, then I can just use that. Why wouldn't I just use that for a spacesuit? Because I was coming up with a spacesuit design. I was like, all right, so I have this copper thread that's hollow that allows for water to go through it, weaved in a particular, cross up down pattern. But then it's like, right. Caveat: I need to put on this self-regenerating crystals that also allow for electricity to flow through it. On cars, they put them on cars. The paint. It's a crystalline paint that will regenerate a scratch or two. And I was like, it's bendable enough. When done like this, it should work, especially when doped with the right material. And it can have piezoelectrics through it, which will allow for the expansion and contraction and generation of electricity. Then it's like, then I wove, those hazmat suits, like the plastics that they use. It's like, then if you really make them thin, and then you put in what was it that we used? It wasn't iron. Or not me. There's no we, it's just me. But the point is I used a, what the hell was it? It wasn't iron. It wasn't titanium. But they were these threads of metal. I think I used not silicon. Silicon's too brittle. Shoot. It was magnesium. Point is, it was a metal that I wove together and twisted it, and then then I was like, all right, a hydraulic fluid that's a non-Newtonian-ish fluid that allows for transfer of electricity through it. And it basically is an oil that allows for electricity. So oil usually is an insulator, but there are oils that are the opposite of insulative and are hydraulic fluids. And so it's when I do that with this material, that was essentially a interspacing of these in between these cross up and down weave patterns. And then plates, effectively, they wrap around it, so that way it's muscle, bone, and sinew. And so they're fairly stiff for what they are, but it's mostly form-fitting, and you can move it around quite easily. And it's oh right, the fluid would help slow down, and the paint, and then the water, and then I can create charge fields and electromagnetics because I have copper and all this other stuff. It's the compound. I forgot what the hell that compound was. I should have wrote it down. I never wrote it down. I was just doing it in the old, right there, you see. I was just sitting down and thinking about it. But I did it back when I was in my parents' house in Chandler as well. And so, anyways, I managed to, what was it? Shoot, what was it? It wasn't iron. We can't use iron. It was a silicon. No, it wasn't silicon. Sheesh. Anyways, point is, it doesn't really matter. I'm sure there are better compounds, but iron was a decent enough one. We used some basic alloys of because it's iron is fairly dense for what it is, but I don't want it to be very dense. But it's shoot. Anyways, point is, that then went into a bunch of piezoelectric coils of these, which not